This lesson actually has several goals, but I want to start off by defining something called a definite integral. Recall that we've already defined the indefinite integral to be basically the antiderivative of a function f, and we use the capital F to symbolize the antiderivative, and we introduce the integral sign. We've already done that. Now we need to develop a little bit more notation before we can define the definite integral. And here's the notation I'm talking about. If we write a function and then put numbers that represent what we'll call limits of integration to the right, in this case I've indicated them a and b. When I write it like that, that means to take the top number and plug it into the function, and then take the bottom number, plug it into the function, and subtract the two results. That's what this notation means, and you've got to learn that. It's just once you get it in your head, it becomes second nature. Now, having said that, what I'm really saying is that new notation simply means take the top limit number, whatever you want to call it, plug it in, take the bottom number, plug it in, subtract the two results. For example, if I gave you this expression x squared minus 2 and put it in that notation with the limits 1 and 3, 1 being the bottom number, 3 being the top number, all you do is take the top number, this time being a 3, plug it in place of x, and so you get, instead of x squared minus 2, you get 3 squared minus 2. Then you take the bottom number, this time a 1, and plug it in place of x, and you get 1 squared minus 2, and then you subtract those two results. So of course 3 squared minus 2 is 7, 1 squared minus 2 is negative 1, and you've got a minus, so that becomes 7 plus 1, which is 8. You're going to be doing this over and over again, so it's a skill you need to practice. It's nothing but a skill. You read the notation, remember what it means, and then practice plugging the numbers in. It's just a skill that has to be developed. But now we're ready, with that notational bit of information added, to define what we'll call the definite integral. The definite integral is defined to be, it's the same symbology we use for the indefinite integral, except we've got these numbers a and b added to the integral sign. Those are called the limits of integration. A is the lower limit of integration, b is the upper limit of integration. And what it means is, you take the antiderivative of the function, just like we did with an indefinite integral, but instead of adding plus c, you evaluate it from the lower limit a to the upper limit b, which we just learned means taking the top number, plugging it into the function, then taking the bottom number, plugging it into the function, and subtracting the results. So the definite integral takes the antiderivative just like the indefinite integral does, but instead of putting a plus c and saying that's the general antiderivative, we actually get a numerical answer by evaluating according to that formula that we learned a few minutes ago. Again, it's just a skill you have to practice after learning the basic notation and definitions, and then it becomes just practicing the skill, and the skill involves taking an antiderivative and evaluating it for two numbers and subtracting. And again, practice is the key. This result is actually so important that it's called the fundamental theorem of calculus. Given some basic conditions, this integral, which is the antiderivative evaluated from the lower to the upper limits of integration, upper limit value evaluated, lower limit value evaluated, subtracting the results, that's called the fundamental theorem of calculus. Now let's just look at some examples. Having introduced this notation and this new idea of a definite integral, it really comes down to just being able to recognize a definite integral when you see it, understanding what it's asking you to do, and then practice doing it. So let's just do one. If I gave you this definite integral, the integral of 3x dx evaluated from 4 to 6, what do? Well, according to the fundamental theorem, you take the antiderivative of the function. So the antiderivative of 3x, we've been practicing that for some time now. Just let the 3 sit there, and then you've got the power of x being 1 raised up to 2, and then you multiply up front by a half, and of course 3 times a half is 3 halves. I hope that skill has already been practiced and you're pretty good at that already. In any case, you take the antiderivative and then you evaluate it over the limits of integration, so it's from 4 to 6. How do you do that? According to the fundamental theorem, you put the 6 in first. That 6 gets squared and multiplied by 3 halves. Then you plug the lower limit in, which is the 4, so the 4 gets squared and multiplied by 3 halves. Of course, 6 squared is 36, and 4 squared is 16, and 3 halves times 36, if you cancel the 2 into the 36, you get 18, and the 2 into the 16, you get 8, and you end up with 54 minus 24, which is 30. The idea is pretty simple. You recognize the antiderivative from the basic definite integral. You find that antiderivative, you evaluate it according to the fundamental theorem, and then it's some arithmetic, and you come up with the answer. And again, practice is the key. Let's do another. Now this says the integral of 2 over x from 1 to 3. Now we probably recognize that 1 over x thing as being the signature of something that integrates to a natural log, but that 2 can just be brought out front so you can see that it's really a 1 over x. You can always take a constant factor out, and again, I think we've practiced that enough before that doesn't seem odd. And now you get the integral of 1 over x, which we know to be the natural log of the absolute value of x. That's one of the formulas we learned. That 2 is still there, so it's 2 times the natural log of the absolute value of x, and we're evaluating it because it's a definite integral. We're evaluating it from 1 to 3. What does it mean to evaluate from 1 to 3? You plug the 3 in, you plug the 1 in, subtract the results. So I'm just going to put the 2 out front and let it just go along for the ride. When you plug 3 in for x, you get the natural log of the absolute value of 3. When you plug 1 in for x, you get the natural log of the absolute value of 1. And again, that 2 just goes along for the ride. Now, if you remember, the absolute value of 1 is just 1, and the natural log of 1, according to your log properties, is 0. So that simplifies things nicely. And of course, you really don't need an absolute value sign around a positive number, so you can actually drop that as well. And so you end up with 2 times the natural log of 3. So we've done a couple of definite integrals, and you can see that it's nothing vastly new. You've got some new notation to interpret. You have to still do the same antiderivatives you were doing before, and then you've got a little bit of arithmetic work to actually use the fundamental theorem and get a final result. Notice that you get a numerical answer when you do a definite integral. Now, I would say right now, so far so good. There is one other thing I want to mention, and that is sometimes the integral is complicated enough that you need to do a substitution. And if you have to do a substitution with a definite integral, there is an extra thing to consider. If you put in a u and substitute to do a substitution for a definite integral, you're going to be replacing the x's in the integram with u values. The x integram will come out, the dx will come out. But now think about this a minute. These values for the definite integral are actually x values, so you have to deal with those too, and that's what this extra care has to be taken into consideration when you're doing them. And it's probably better just to go through an example to show you what I mean. You have a little extra thing to worry about when you're doing a substitution with a definite integral because you have those limits of integration to worry about. And it's best to illustrate through a simple example. Suppose I ask you to compute this definite integral. It's the quantity x minus 2 squared. And I want to find that definite integral from 1 to 2. Think about this a minute. We don't normally put a label on those limits of integration to say they're x values, but because we're going to be changing from x's to u's, I want to actually take the step of labeling those things and saying, now that 1 is an x value and that 2 is an x value. And I'm going to do that by explicitly saying it, that 1 is really an x and that 2 is really an x. And the reason I'm saying that is if I'm going to do a substitution, not only do I have to worry about getting rid of the x's here and here, I've got to get rid of the x's here and here as well. And that's the extra thing you have to worry about when you're doing a substitution with a definite integral. But it's not difficult. Let me show you. Start off just like you normally do. I'm going to let u be x minus 2. The differential then will be 1 dx or just dx. And so it's going to be nice. This is going to come out as the u, so I'll have u squared. This will come out as du. That'll be easy. But those x values on the limits of integration have to be changed to u values. So the extra step you have to take when you're doing a substitution with a definite integral is you have to go in and calculate what happens to the x value when you change to u's. So if you start out with this lower limit x equal 1 and you plug that in for x in the relationship between u and x, you find out that u is going to be minus 1. So when x is 1, u is minus 1. Then you do the same thing for the upper limit. When x is 2, if you plug 2 in for x, you get 2 minus 2 is 0. So when x is 2, u is 0. So these limits that used to be 1 and 2 that were x values now are going to become u values. So the 1 turns into a minus 1, and the 2 turns into a 0. So when you change from x's to u's, not only does the x minus 2 have to change to u, and that gives me 2 u squared, and the dx change to du, the limits of integration have to change as well. But it's easy. Now once you do that, it's just a normal integral that you've done before, or an antiderivative that you've done before. The antiderivative of u squared is 1/3 u cubed. We're evaluating them now on u from minus 1 to 0. That means you put in the top limit first, that's a 0. Then you put in the bottom limit, which is minus 1, and then you subtract the 2. Be careful with the signs. Of course, 0 times anything is 0. 0 cubed is 0. Everything zeroes out in the first term. So all you're left with is this second part. Now the second part, when you cube a minus 1, you get minus 1, and you get minus a minus, so that turns into eventually be a plus. And the answer is 1/3. That's a definite integral where you need to do it by substitution. And this is actually the way I recommend doing it. I do want to say, and I mentioned earlier, there is an alternate way of doing this, and that is to just go back to your x's before you do the limits of integration. Notationally, that's a little more difficult to pull off. It looks funny as you write it out notationally, but in practical terms, it might even be easier. It's certainly no harder. And I'll show you what I mean. If you really want to avoid having to do this part of the calculation here, where you're actually calculating how the x values change into u values, what you can do is when you get down to the point where you found the antiderivative in terms of u, just write that down and then get rid of the u. Just put the x's back in. Well, we know that u is x minus 2, so just put the x minus 2 back in. And if you do that, you can go back to the original x values and evaluate from 1 to 2 instead of evaluating after we changed before. So that's an option. And if you plug in a 2 and do the calculation, then plug in a 1 and do the calculation and subtract the 2 results, you'll get the same answer. It's just a matter of which you prefer. So my suggestion is to just pause everything, try to do this integration just like I did it in the first method. See if you can follow step by step and come up with the answer of 1/3. Once you're solid on that, then go back and try to do it again using the second method. Practice it till you get solid on it, and then decide which way you like best. Either works, either gives you the same answer, but you need to decide which makes the most sense to you, or which you like better, or maybe it comes down to just which you're less likely to make a careless mistake on. It's not difficult, but it does require practice. Okay, now that we've learned how to define definite integrals, we're going to put that on pause. We're going to put it aside for just a short period of time and go to something else that looks totally different. But believe it or not, in a few minutes there will be a connection, and we'll come back to the definite integral, and it will come into play in a really kind of remarkable way. But for now, let's just put aside this definite integral. We're going to use it again in a few minutes, but for now, put it aside, and let's do something that looks, at least at the beginning, something totally different. And that has to do with determining areas under curves. And it turns out that doing that is one of the most important applications of integrals, antiderivatives. And you're going to see that as we go through this process. But even now, I want to start off with cases that are so simple that you don't even need the calculus to do. We're talking about areas under curves, but let's do it with functions that are so simple that we don't even need calculus to do it, and then we'll work our way up to where the calculus comes in. So start off with really simple. Suppose I give you a function f of x equals 3. Now remember, that's y equals 3. That's a horizontal line going through y equals 3. And I want the area under that curve from 1 to 4. It's pictured over here to the lower left. And you can see that y equals 3 is just a horizontal line going through 3 on the y-axis. And if I want to go from 1 to 4 and look at that area, it just comes out to be a rectangle. And we're looking for area. Well, you learned how to use geometry to find areas of rectangles ages ago. What's the area of a rectangle? It's just length times width. So look at the drawing here and figure out what the length and width are. If you think about it, this f of x equals 3 means it goes up to height 3, so that height of the length or width, whichever you like to call it, of that rectangle is 3. But then you're also going from 1 to 4. That's also a length of 3. So actually that rectangle is a square. The area is just length times width. That's 3 times 3, and the area is 9. So some of these area problems you could actually do without knowing any calculus if it turns out to be a formula that you learn from geometry to find the area. And it's not just squares and rectangles. What if you have this function? If I gave you the function f of x equals 1/5 x, that's just a line with a slope of 1/5 and a y-intercept of 0. If you were to plot a couple of points, you can see what it looks like. It looks just like this picture. And you want to find the area from 0 to 5. So you're starting over here at 0 and you're going to 5. Well, you can see that's a triangle. We know how to find the area of a triangle. The formula for the area of the triangle is 1/2 base times height. Well, what is the base and height? Well, the height is obviously 1. If you go to 5 and plug 5 in right here, you get 5 times a fifth is 1, and also you can see it just from the picture. The base is going from 0 to 5. That's a distance of 5 as well. So 1/2 base height, 1/2 times 5 times 1, that just comes out to be 5/2 or 2.5. Again, we were able to find that area using geometry. Let's do one more where we can slip a little geometry in and get an answer without doing any calculus. Suppose I give you the function f of x equals the square root of the quantity 4 minus x squared, and I want to go from -2 to 2. That's just the top half of a circle. If you take that y equal the square root of the quantity 4 minus x squared and square both sides, you'll see that it's just a circle, and we're doing just the top half of it, because the whole circle would actually be, the top half of the circle is a plus. If you took the minus part, that would be the bottom half of the circle. But there is no minus here, so we're just dealing with the top half of the circle. But anyway, you can see it from the from the graph, if that wasn't the first thing you thought of when you saw that equation. Bottom line is, we know how to find the area of a circle. Actually, we only want the area of a semicircle, half the circle. The area of a circle is pi r squared, so the area of just half of the circle is going to be 1/2 pi r squared. Well, what's the radius of the circle? The radius of the circle is 2. So you plug a 2 in for r, square it, take half of it, and multiply by pi, and you end up with 2 pi. So again, we found the area under that curve without using calculus because we knew some geometry. By now, it probably occurs to you, what if we want to find the area under some curve and we don't know anything about the geometry that will allow us to find the area? This is where the calculus kicks in, and I'll show you how. It's really pretty remarkable, actually, that it ties back to that fundamental theorem of calculus that we just covered. I told you we'd come back to it, but this is where we come back to it. And here's the tie-in. For any function f that satisfies that condition to that fundamental theorem of calculus, the definite integral, we define that to be the definite integral. The definite integral gives the area under the curve from A to B. That's pretty remarkable. Why is that true? We're not getting into that, but it's actually pretty remarkable that you can find the area under curve using the fundamental theorem of calculus. And let's just go through and I'll show you how simple it is if you can do the definite integrals. Once you understand how to do definite integrals and get good at them, finding areas under curves is really quite easy. Suppose I gave you y equal x squared plus 1. I drew a picture of it over here to the right, and I want to find the area from -3 to 3. Well, according to what I just said, all you have to do is use the fundamental theorem of calculus on it, and in this case a would be -3 and b would be +3, and do the antiderivative, which leads you to get the definite integral. So I'm going to take the integral of x squared minus 1 evaluated from -3 to 3. That means I take the antiderivative. The antiderivative of x squared is 1/3 x cubed. The antiderivative of 1 is x. Evaluating from -3 to 3, that means plugging in the top number, then the bottom number, and then subtracting. The main thing here is being very careful, especially about signs. So when I cube 3, I get 27. When I cube -3, I get -27. Be very careful with the signs here. 1/3 of 27 is 9, and 1/3 of -27 is -9. Use parentheses properly and be very careful with signs because it's easy to make a mistake. So in the first set of parentheses you get 12, in the second set of parentheses you get -12, but it's minus a -12, which means +12, which means the answer is 24. And as I said, if you're good at doing definite integrals, finding the area under the curves is really just easy. It does take practice, but the idea is very simple, as well as being remarkable. You might have noticed, I don't know if you did or not, there's a symmetry in this graph. If you were to cut it right at the line x equals 0, the left half of that graph looks just like the right half of the graph, which means half the area is to the right of 0 and half the area is to the left of 0. If you ever notice a function that's symmetric like that, you can just integrate from 0 to the right-hand endpoint and just double your answer. So you can just try to find the area to the right and realize, well, that's just half the right answer and double it. So another option, if you notice symmetry, it doesn't always happen, but if you do notice symmetry, you can just double the answer as if you started from 0 instead of -3. And sometimes that calculation, in fact quite often, that calculation is much easier. Plugging zeros in tend to be easier. So if you did it that way, the antiderivative would be the same, and you start off the same way by plugging 3 in, but then when you plug 0 in, that whole second part just vanishes because 0 times all that just goes to 0, and the calculation becomes a little bit simpler. But you do get the same answer either way. You don't have to notice the symmetry to work the problem, but if you do notice that type of symmetry, it's perfectly okay to take advantage of it. totally up to you. Let's do another one with symmetry. Suppose I'm giving you this one. That actually happens to be the graph of y equals 16 minus x to the fourth. And again, you can see that same symmetry. I'm going to do it both ways. If you just completely ignore the symmetry, you're going to use the fundamental theorem again. You're going to integrate the function from minus 2 to 2. Minus 2 to 2. Take the antiderivative of 16, you get 16x. Take the antiderivative of x to the fourth, you get 1/5 x to the fifth. You evaluate from minus 2 to 2. That means plug the 2 in first, then plug the minus 2 in, and then subtract the results. Be very careful with the signs and with the arithmetic. 16 times 2 is 32. 16 times minus 2 is minus 32. 2 to the fifth is 2 times 2 times 2 times 2 times 2, which is 32. So you get 32 times a fifth, which is 32 fifths. Just be careful. And on this over here, you're going to get a minus times a minus, so you'll have a plus. So this sign in here is negative, and this sign here is positive, and then you've got a minus between the two. So many opportunities to make careless mistakes. Take your time. But anyway, if you do all that, multiply that all out, if you distribute that minus sign, that changes to a plus, and that changes to a minus. And then, of course, 32 plus 32 is 64. And you get a minus 32 fifths minus another 32 fifths, and that's a minus 64 fifths. And then if you get a common denominator by multiplying top and bottom of 64 over 1 by 5, you'll get 256 fifths. A little bit of arithmetic, but not bad. As I said, though, if you notice the symmetry, you don't have to notice it, but if you notice that half the area is on one side of the graph, half the area on one side of the graph is the same as the area on the other side, you can just go from 0. Instead of going from minus 2 to 2, you can go from 0 to 2. And if you do that, you get the same setup for the integration. And it's not until you get to the point of plugging in that second number that anything changes. And you just have everything becomes 0. And so you don't have as much arithmetic to do. 16 times 2 is still 32 like it was before. 2 to the fifth is still 32 times a fifth is 32 fifths. And then you get a common denominator. 32 over 1 is 160 fifths. 160 minus 32 is 128. But you're doubling it. Remember, all the way down, you're doubling it because the actual area you're looking for is twice as much as what you're finding, and that gives you 256 fifths. And notice that's exactly the same answer as before. I would suggest, if you haven't already done this, is to pause everything now and go back and work through these last couple of problems and do them both ways. Go slowly, take your time, make sure you understand every step, and keep at it until you've successfully done it. Practice, practice, practice. Now, everything's not symmetrical. And if I ask you to find the area pictured on the graph of y equals 5 over the square root of x, you can see from the graph that that's not symmetrical at all. So this time you don't have an option of doing symmetry. You're going to have to do it from 1 to 25. So you set up the integral. Remember that the square root of x is x to the 1/2. And if you take that x to the 1/2 in the denominator and push it up, it becomes x to the minus 1/2. And we know how to integrate that. You think of the 5 as just coming out front, so you can just let it ride along. And when you integrate x to the minus 1/2, you add 1 and divide by it. Well, if you add 1 to minus 1/2, you get a half, so you get a power of a half for the x, and then you multiply up front by 1 over a half. Of course, 1 over a half is just 2. Of course, 2 times 5 is 10, so you get 10 times the square root of x evaluated from 1 to 25. Easy enough. You put in the top number, which is 25, so you get 10 square root of 25, minus, then you plug in the bottom number, which is 1. Square root of 25 is 5, so you get 10 times 5 is 50 from here, minus, and then 10 times square root of 1 is 1, 10 times 1 is 10, so you end up with 40. Again, no symmetry involved, so there's no alternate way to do this, but the process is very straightforward. Another example of the use of a definite integral is in marginal analysis. In other words, you know the marginal cost of some product, or the marginal revenue of some product, or the marginal profit of some product, and you want to figure out the exact increase or decrease in your either cost, revenue, or profit, depending on which function you're working with, obtained by selling maybe just one additional unit or possibly multiple additional units. And that has to do with the definite integral, because you're going from marginal back to the total. You're either going from marginal revenue to total revenue. That's an integral. Going from total revenue to marginal revenue is derivative. So going from marginal to total is the definite integral in this case. So I'll show you how simple this is with an example. Suppose I give you the marginal revenue of some product, the derivative of the total revenue with respect to x, where x is the number of units, and that is 50 minus 2x. And here's the question. Find the change in revenue if sales increase by 2 from a current level of 10 units. In other words, you're going up by 2 units. What is that going to do to your revenues? Well, you're going from 10 to 12 if you're going up by 2. It's a definite integral, as I said, so you take the marginal, in this case marginal revenue, and you find the definite integral from 10 to 12, because you're at a current level of 10 and you're increasing by 2. If you're at a current level of 18, you're increasing by 5, it'd be 18 to 23. Now, as it turns out, those two antiderivatives, those two integrals of that multi-term expression here are very easy. The integral of 50 is just 50x, because the derivative of 50x is just 50, and the integral of 2x is just x squared, because the derivative of x squared is 2x. It's not always that simple, but for these problems we're going to keep it fairly simple, and in this example I made it especially simple. But in any case, the antiderivative, or the integral of 50, is 50x, and the antiderivative or integral of 2x is x squared, and there's a minus sign between them, and we're going to evaluate it from 10 to 12. What do? You plug in the 12, so that you plug the 50 times 12 minus 12 squared. Then you put a minus sign, and you plug in the bottom number, which is 50 times 10 minus 10 squared. Be very careful to use your parentheses and brackets, however you want to write it, because if you don't, that minus sign in between them is going to cause you to make a mistake. It's minus the entire expression to the right of it. Now it's just a matter of simple arithmetic. 50 times 12 is 600. 12 squared is 144. 50 times 10 is 500. 10 squared is 100. 600 minus 144 is 456. 500 minus 100 is 400. And 456 minus 400 is 56. And this is in dollars. So in this case, if that's your marginal revenue function, the change in revenue, if your sales go from 10 to 12 units, would be $56. Just a simple example related to business.